Good day. We are from Group 4. We will be presenting about corrosion of onshore piping system. My name is Logramna Subramaniam. Today I am going to present about introduction. Corrosion in onshore piping system is a widespread and serious problem. It can negatively impact the structure's dependability, safety and life expectancy. Onshore piping systems are used in various sectors such as oil and gas, petrochemicals, water treatment and power production. Corrosive elements like moisture, oxygen, aggressive chemicals, temperature fluctuations and soil conditions contribute to the corrosion process. Negative consequences from corrosion include pollution, economic losses and injury to human life. Corrosion affects fluid flow efficiency, increase energy consumptions and requires costly repair and maintenance. Preventative techniques include using corrosion-resistant materials, protective coatings and linings, cathodic protection systems, corrosion inhibitors, and regular inspection and maintenance. Proper corrosion management techniques and practice are crucial for reducing the impact of corrosion, increasing the lifetime of pipe systems, and ensuring safe and dependable transportation of fluid and gases onshore.
My name is Lograshni Subramaniam and today I'll be presenting question number 1, 2 and 4. Based on question number 1, provide statistical data about the failure related. Based on the article that we have discussed, the significant consequences of unintentional release from buried gas pipelines primarily attributed to corrosion and external interference. The study highlights the importance of pipeline characteristics for protection against corrosion and external interference. Based on the Bayesian network model, estimates failure frequency, leakage size, and critical parameters in pipeline failures. Construction year, material, cover diameter, and depth are crucial for preventing failures. The article also recommends daily maintenance and overhaul to enhance the pipeline safety management. The figure at the side shows the corrosion failure frequency validation result from the year 1974 to 2016. Moving to question number 2, what are the damage mechanisms and spot locations? Corrosion such as general corrosion, pitting corrosion, stress corrosion cracking (SCC), crevice corrosion, microbiologically influenced corrosion (MIC) have been diagnosed. General corrosion is the most common type, causing metal to weaken equally over time in pipes exposed to moisture, chemicals or corrosive gases. Pitting corrosion is actually caused by aggressive compounds like chloride ions, creates tiny holes on metal surfaces, especially on pipes, outer surfaces, especially when welds or joints are present. Stress corrosion cracking (SCC) caused by tensile tension and corrosive environments which can cause fractures and pose a serious threat to pipe systems. It often in high stress areas or corrosive environments. Crevice corrosion commonly occurs in small cracks or niches influenced by oxygen deficiency or stagnant conditions, causing damages to flanges, fittings, deposit and gaskets. Moving to the last, microbiologically influenced corrosion (MIC). It occurs in stagnant, biofilm active regions such as underground pipelines and cooling water systems, which can cause severe rusting.
Question 3. Predict what other loss may happen if a corrosion monitoring program is not conducted. Number 1. Failure of equipment. Failure of equipment due to unnoticed corrosion can lead to accidents, spills, and operational interruptions. Number 2. Product contamination. Corrosion-related product contamination in storage tanks or pipes can result in environmental damage, quality issue, and safety risk. Number 3. Increased maintenance. Lack of a monitoring program increases maintenance costs as corrosion progresses unchecked. Number 4. Reduce asset lifespan. Corrosion reduces the lifespan of assets and infrastructure, resulting in inexpensive repairs or premature replacements. 5. Negative reputation and customer trust. Corrosion-related breakdowns and accidents can harm a company's reputation and erode customer trust. Number 6. Safety risk. Corrosion-related failures pose safety and environmental hazards such as fires, explosions, and hazardous discharge. Number 7. Environmental damage. Environmental damage from corrosion related leaks or spills require significant cleanup efforts and can lead to legal consequences. Number 8. Loss of data insight. Without a corrosion monitoring program, valuable data and insight of corrosion rates and prevention techniques are lost. Number 9. Decreased operational efficiency. Corrosion impedes fluid flow and decreases operational efficiency, leading to lower productivity and increased energy consumptions.
Next, based on question number 4, identify the parameters affected corrosion on an onshore piping system. Flow properties, pH, dissolved oxygen and corrosive ions affect the process, causing general and localized corrosion. Alkaline liquids promote passivation, while higher dissolved oxygen increases corrosion rates. Moving to the next point, which is material selection. It is crucial for determining corrosion susceptibility in above ground piping system. Different materials offer varying resistance and selecting materials with high resistance for specific environment, which can actually reduce the corrosion severity. And the third point is design consideration and operating parameters. Pipe diameters, thickness, fluid flow, and joints can affect corrosion. Proper design, fabrication, and surface treatment minimize voids and ensure reliable welding practices. Environmental factors, high humidity, moisture, and exposure to corrosive gases significantly impact pipeline corrosion. The atmospheric conditions, industrial processes, and high dust level contribute to corrosion risk. Lastly, coating. Using surface coating like epoxy, polyethylene, or FBE for improved corrosion resistance on pipe surfaces and inner tubes to protect against transported liquid corrosions are also very essential. Thank you.
Hello, today I would like to present about the corrosion prevention suggestions. So the first suggestion is the cathodic protection. So cathodic protection safeguards the piping by making it the cathode in an electrochemical cell, diverting the corrosion reactions away from the metal surface. So there are two types of cathodic protection methods which is commonly used for onshore piping. So the first one is the sacrificial anode protection, which these methods corrodes preferentially instead of the piping material, offers protection. Zinc, aluminum or magnesium are common materials used for the anodes, possessing a more electronegative electrochemical potential than the piping material. When the anodes are electrically connected to the piping, they generate a galvanic current that flows from the anodes to the piping. This current counteracts the corrosion reactions on the piping surface, providing cathodic protection. Over time, the sacrificial anodes gradually corrodes and necessitate periodic inspection and replacement. So the second type is the impressed current cathodic protection method, which employs an external power source to deliver a direct electrical current to the piping. The current is introduced to the piping through anodes typically made of high quality graphite, mixed metal oxide or platinum coated titanium. These anodes are distributed along the pipeline and connected to a power supply. The impressed current establishes a protective electrochemical environment on the piping's surface, inhibiting corrosion. The current output is regulated and monitored to ensure sufficient protection. So both sacrificial anode and impressed current cathodic protections offers advantages and consideration. The choice between the two depends on the factors such as environment, soil resistivity, coating condition, pipe to soil potential requirements, and economic consideration. So the second suggestion is to prevent corrosion on onshore piping. We can use various protective coatings can be applied on the surface of the pipes. So the first is the fusion bonded epoxy coatings, which are thermostatic epoxy powders that undergo application onto heated pipe surface. Upon curing, the epoxy melts, result in a continuous, resilient and corrosion-resistant coating. The second one is the polyethylene or polypropylene coatings are commonly utilized for buried onshore pipelines. These coatings are applied as extruded or hot applied tapes, which are then heat shrunk and fusion bonded to the surface of the pipe. They offer favorable resistance to soil, stress, abrasion, and chemicals. The third one is the coal tar enamel coatings, formulated with coal tar pitch, are applied to the heated pipe surface. Upon cooling, The coatings forms a dense and impermeable film, providing protection against soil corrosiveness. So coal tar enamel coatings have a long history of usage and demonstrate a very good resistance to soil, water and certain chemicals. Next is the liquid epoxy coatings, which encompass solvent-based or water-based epoxy formulations that are either spray applied or brush applied on the pipe surface. These coatings undergo curing to establish a tough and chemical-resistant film. They exhibit reliable adhesion, flexibility, and resistance to impact and abrasion. So the next one is the polyurethane coatings. Consists of solvent-based or water-based formulation that serve as top coats applied over epoxy or other primers. Polyurethane coatings provide enhanced durability, often finding application in the above-ground piping or outdoor environments. The last one is the zinc coating, such as hot dip galvanizing or zinc-rich primers, delivers both barrier and sacrificial protection. These coatings establish a protective layer that sacrificially corrodes before underlying the pipe material as affected. Zinc coatings prove effective for atmospheric as well as burin application. So the third suggestion is the material selection, where material selection for onshore piping is crucial for preventing corrosion. The primary purpose of material selection is to ensure that the chosen material can withstand the corrosive environment to which it will be exposed. Corrosion can lead to pipe degradation, leaks, failure, posing safety risks, environmental hazards, and significant financial implications. So by selecting the appropriate corrosion resistance and likelihood of corrosion related issues can be minimized. Furthermore, longevity and reliability of important because onshore piping systems are designed to have long service lives. So choosing the right materials with good corrosion resistance can extend the life of expectancy of piping, reduction in the need of premature replacements and minimizing downtime and associated costs. It also enhances the overall reliability of the piping system, ensuring uninterrupted operation. So the fourth one is the design consideration, where a proper pipe design can minimize the risk of corrosion. Consider the following design factors. The first one is to minimize dead legs and stagnant areas where fluids can accumulate. The second one is to avoid sharp changes in direction that can promote erosion or localized corrosion. The third one is ensure proper drainage to prevent water accumulation. And the last one is to allow the sufficient spacing and support to avoid contact with other metals that can induce galvanic corrosion. So the fifth suggestion is the monitoring and inspection, where it plays a crucial role in maintaining the integrity and reliability of the piping system. So the first monitoring and inspection is the early detection of corrosion is important, where the regular monitoring and inspection allow for the early detection and corrosion related issues. By implementing a systematic monitoring program, potential corrosion problems can be identified in their early stages before they escalate to major issues. The second is timely detection for corrosion allows to proactive maintenance and preventive measures to be taken. By addressing corrosion at an early stage, organization can prevent further damage, extend the life of the piping, minimize the need for costly repairs or replacement. And the third one is the safety and environmental protection is important issue since the corrosion related failures in onshore piping can have a severe safety and environmental consequences. Leaks or ruptures due to corrosion can result in a hazardous situation leading to accidents, injuries and environmental contaminations. The fourth one is the cost optimization, where timely detection and proactive management of corrosion through monitoring and inspection can lead to cost savings. By addressing corrosion issues early on, organization can avoid costly repairs, replacement and unplanned shutdowns. And the sixth suggestion is to maintain the corrosion resistance of offshore onshore piping. It is important to implement effective maintenance and repair practices. Here are some considerations for maintaining and repairing onshore piping. So the first one is to regular cleaning the pipings to remove debris, sediment and fouling that may promote corrosion. The second one is regularly inspect the protective coating applied on the piping and look for the signs of coating such as peeling, cracking or blistering. The third one is the cathodic protection maintenance must be done, where if a cathodic protection systems are installed, ensure their proper operation through regular monitoring and maintenance. This includes measuring pipe to soil potentials, inspecting the sacrificial anodes or impressed current anode systems. The fourth one is implement leak detections, where it measures to identify any potential leaks or breaches in the piping system. Early detection can prevent the corrosive substances and minimize the risk of localized corrosion. The next one is the repair the corroded areas if corrosion is detected on the piping. Take an appropriate measures to repair the affected areas. This may involve removing the corroded material, applying corrosion inhibitors or protective coatings, or replacing the damaged section of the piping. The last one is the continuously monitor the corrosion related parameters such as pipe to soil potential, coating integrity, corrosion rate. Analyze the collected data over time to identify trends, corrosion hotspots, areas required targeted maintenance or additional corrosion methods. The last one is to maintain the accurate records of maintenance activities, repairs, inspection results, and any corrosion related incidents. Thank you.
Hello everyone, my name is Arvind, son of Ganasekaran. My metric number is CD190325. So, based on the question that I have been given, now I will be discussing about question number 6, which is identify standards for inspection and measurement. So, as you can see, we have a few standards, which is API 570, API 653, ASME B3 1.4, and also 1.8. So, in API 570, it is created by the standard for inspecting, repairing, modifying, and rotating in-service piping system. It sets guidelines for inspection techniques, frequency, and qualification of participants. For API 653, it focuses more on inspecting, repairing, altering, and rebuilding above-ground storage tanks. It also provides recommendation for inspecting adjacent piping systems. For ASME B3 1.3, this standard specifies design, construction, and inspection standards for processing piping systems. It covers material fabrication, inspection, and also testing. For ASME B3 1.4, it focuses on liquid transportation system for hydrocarbon, liquid petroleum gases, anhydrous ammonia, and also alcohol. It specifies design, construction, inspection, and testing requirements for these piping systems. Well, finally, for ASME B3 1.8, the standards applies to gas transmission and distribution piping systems, including onshore gas pipelines. It specifies design, construction, operation, maintenance, inspection, and integrity management requirements.
So now I would like to predict the material of construction to respective failures. The first one is the stainless steel, which is renowned for its exceptional corrosion resistance attributed to the presence of chromium, which forms a protective oxide layer on the surface. Different grades of stainless steel are available, each offering varying levels of corrosion resistance, strength, and cost. Austenitic stainless steel is frequently employed on a broad range of onshore piping applications. So the next material is the corrosion resistant alloys are specifically engineered to withstand corrosive environments. These alloys incorporate elements like nickel, chromium, molybdenum, and copper, which enhance their resistance to corrosion. So the commonly used corrosion resistant alloys include Inconel, Hastelloy, Monel, and Duplex stainless steels, and often chosen for highly corrosive settings such as offshore and chemical processing application. The third one is the high density polyethylene and polyvinyl chloride exhibit a favorable corrosion resistance. These materials are particularly suitable for application involving water distribution, sewage system, chemical processing, where corrosive substances are present. Plastic piping possesses an advantages of being lightweight, easy to install, and resistant to both internal and external corrosion. The next one is the fiberglass reinforced plastic piping. Consists of a resin matrix reinforced with fiberglass strands. It demonstrates excellent resistance to corrosion, chemicals, and extreme temperatures. So the fiberglass reinforced plastic commonly used in industries such as oil and gas, chemical processing and water treatment. So the last one is the ductile iron with protective coatings, where these pipes can utilized for onshore piping when appropriate protective coatings are applied. These coatings acts as a shield between the metal surface and the surrounding environment, thereby enhancing the longevity of the pipe. Thank you. Hello, so now I would like to present about the method of inspection for the corrosion. So the first method is visual examination, where it is the most fundamental and widely utilized technique for keeping track of onshore piping corrosion. The piping systems is visually inspected by trained workers to look for corrosion indicators such as rusting, pitting, scaling, or coating degradation. Visual inspection can be carried out as a part of regular maintenance tasks or during routine walks around the piping infrastructure. So the next method is the non-destructive testing techniques, which are utilized to assess the condition of onshore piping without causing damage. So the first type of NDT is the ultrasonic testing, where they employs high frequency sound waves to detect corrosion, thickness variations, and flaws in the piping material. It accurately measures the remaining wall thickness and enabling the calculation of corrosion rates. So the next one is the radiographic testing, where it uses X-rays or gamma rays to capture the images of the internal condition of the piping. It can identify corrosion, erosion, and other defects that may not be visible externally. The next NDT method is the magnetic flux leakage, where it utilizes magnetic fields to detect corrosion and metal loss in ferromagnetic piping. So magnetic flux leakage tool is passed along the outside of the pipe, and changes in the magnetic field strength indicate areas of corrosion or metal loss. So the next NDT method is the eddy current testing, where it relies on electromagnetic induction to identify surface and near surface defects, including corrosions, cracks, and erosion. It is particularly effective for inspecting non-ferrous materials. So the next method of inspection is corrosion monitoring techniques, such as continuous or periodic monitoring of corrosion related parameters, which can provide valuable insight into the corrosion behavior of the onshore piping. Some of the common corrosion monitoring techniques includes coupon monitoring, where metal coupons made of same material as piping are strategically installed and periodically extracted for analysis. The level of corrosion observed on the coupons provides an indication of the corrosion rate of the piping. So the next one is the electrical resistance probes, where they are used to measure the changes in the electrical resistance of the piping material, which can indicate corrosion activity. They are particularly useful for buried or submerged piping systems. The last one is corrosion rate monitoring. Various electrochemical techniques such as polarization resistance, linear polarization resistance, electrochemical impedance spectroscopy can be employed to estimate the corrosion rate of the piping. So the last method of inspection is the cathodic protection monitoring systems, where they must be installed. This system, the monitoring their performance is essential. Regular measurements to the pipe to soil potentials and current output of the cathodic protection helps to ensure that the desired level of protection is maintained. So it is important to establish a monitoring and inspection plan specific to the onshore piping system based on factors such as environment, piping material, industry requirements, and etc. Compliance with relevant regulations and standards should be ensured, and inspection should be performed by qualified personnel with experience in corrosion monitoring techniques. Thank you.
Next off, we'll be talking about what are the parameters needed for the inspection to be performed. As you can see, we have several points here, and they are visual inspection, corrosion rate, corrosion product, environmental factors, opening circumstances, corrosion monitoring, inspection procedures, past inspection histories, regulatory standards, and also risk assessment. Next up, we are going to talk about what is your suggestion for the characterization of the damage. So, to categorize the damage, there are several methodologies for analyzing the degree of severity of corrosion damage in onshore pipelines that can be used. Here are various ways to describe the rust damage. So we have three main points here. We have corrosion mapping, visual inspection, and non-destructive testing. also known as NDT. So in this non-destructive testing, we have a few testings, which is ultrasonic testing, radiographic testing, magnetic particle testing, liquid penetrant testing, and also eddy current testing. So for ultrasonic testing, it measures the pipe wall thickness and identifies corrosion or thinning. In radiographic testing, it produces image of pipes inside structure, revealing the corrosion related issues. Whereas for magnetic particle testing, it identifies the surface breaking cracks or faults caused by the corrosion using magnetic field and particles. In liquid penetrant testing, it detects the surface cracks or faults by using the dye penetrant. Well, finally, for eddy current testing, it uses electromagnetic induction to detect the surface and near surface corrosion issues. That is all from me. Thank you.
Conclusion. Corrosion poses a significant threat to onshore pipe systems, compromising reliability, safety, and lifespan. A comprehensive corrosion prevention and control strategy is necessary, including the use of corrosion-resistant materials, protective coatings, cathodic protection systems, corrosion inhibitors, and regular inspection and maintenance. Corrosion allowances, fluid chemistry management, and corrosion monitoring systems are crucial in mitigating corrosion risk. Implementing preventative methods and practice reduce the impact of corrosion, prolongs the lifespan of onshore pipe system, and ensures safe and efficient fluid and gas transportations. Ongoing research and advancements in corrosion control technology are important for developing innovative solutions and increasing the longevity of critical infrastructure components. Staying updated on the latest corrosion prevention and control approaches is essential for engineers, maintenance personnel, and operators. Prioritizing corrosion prevention leads to reduced downtime, lower costs for repairs and replacements, and optimal performance of onshore piping system. That's all. Thank you.